Hello, everyone. So we have got everything today. We have got all about future colliders, about the future physics. Viplav has given us enough goals. So let's see what we have to do next with our detectors and what it means for the detectors. So this sort of became a very wide scope. So I sort of limited it and talk about more focused one. So just a disclaimer that the main focus is on the HL-LHC detectors. And of course, it's biased towards CMS, but I will tell about Atlas wherever relevant. And I have not discussed anything about the LHCb or LS upgrades in this talk. So what we want to do with the HL-LHC, almost everything. We want to probe the Higgs sector further. We want to measure the Higgs properties, its self-couplings, and all its rare and exotic decays, as well as the searching for the light zero scalars and much more. And these are the usual pictures we have seen so far in the various talks and various reports, that how much we can achieve in terms of reducing the uncertainties on the various parameters, and also the Higgs to the di-Higgs production in the various channels. Then the HL-LHC will also give an unprecedented opportunity also for the probing the top properties further, and also the precision measurements of all its properties, and also the top and Higgs interplay, precise electroweak measurements, for example, the longitudinal W scatterings. And then we would be able to explore also the complementarity, using the complementarity of the low PT and high PT for the flavor physics, which includes the CChem measurements and also the QCD spectroscopy, radio decays, and flavor anomalies. And the list continues, including what we want to check in the heavy ions, all the precision studies of the material properties of the QCD media, as well as many of the differential measurements. And many of these precision measurements can also open windows to the various VSM scenarios, like what we have seen the activity after this W mass measurements, that what all can go about. And then they also want to go for the direct searches for the new physics, and our usual list of the dark matter, supersymmetry, lepton flavor violation, leptoquarks. The list is very long. And also the resonance searches. Here are some examples I picked up. For example, for the Z prime searches, we can sort of achieve up to like a sensitivity up to like 70 eV particles. And then also not just like these theoretical models, but many of these massive particles as well as the compressed spectra, when the mother particle and the daughter particle, they are very close in mass and they can get very soft decay products, or the long-lived particles. All of these have very sort of increased range when we have the HL-LHC full luminosity available to us for the analysis. So these can benefit a lot from the novel approaches for the analysis, as well as for the better detectors, which can really put the BSM scenarios to the stringent test. So how we are doing all this? Right now, we have this just showing up the CMS detector. The basic idea of these collider detectors is essentially that we have onion-like structure. We have a tracker. In the CMS, we are using the silicon tracker, which is pixel detector as well as the strip detector, which is followed by an electromagnetic calorimeter. This is based on the lead tungsten scintillating detectors, which is followed by the hadron calorimeter. And in CMS, we are using the brass and the scintillator, the sampling calorimeter. And then we have the magnetic solenoid, provide the 4 Tesla magnetic field, which is followed by the Muon chambers. And these are in the CMS, we are using the 3 types of detector technologies, the drift chamber, the drift tube chambers, and the resistive plate chambers, as well as the cathode strip chambers. And now we have also put in the resistive plate chambers, which are used in the Muon detectors. So all is working fine so far. We all know of the run 2 results. Run 3 results have already started coming out. I mean, some of the quick measurements. When you go to the conferences, you see that you can find the first results there. So why do we need to upgrade these detectors? About the HL-LHC plans and all, we have just heard from Marcus. Now, how do those parameters translate to the challenges for the detector, both in terms of the total radiation exposure as well as the high instantaneous luminosities? HL-LHC is the opportunity. That's sort of concrete, that's what we are going to do. And we are expecting integrated luminosity of 3 to 4 atoman inverse, or 3000 to 4000 femtoman inverse. This is just the luminosity curve, which Marcus and in the previous talks also it was presented. These are just the curves of the total integrated luminosity as a function of time. It's basically showing the months for the different years. And you see that, okay, starting from the 2010, how far we have reached the luminosity, and the last one was the 2018, where we had integrated luminosity of 60 femto1 inverse just in 1 year. And run 3 is already surprising us. This was just came as a shock that it was already 30 femto1 inverse when I yesterday checked it. Now, what does it mean in terms of the detector? So here is an example. I picked it for the electromagnetic calorimeter, which was the lead tungsten scintillation calorimeter. It's mainly tuned to measure the electrons and photons, the electromagnetic showers. And what you see here is the sort of relative response as a function of time in the different eta regions, like how forward the detector or in which region of the detector it is. So you see the topmost will be the most central one, while this one is the forward one. So this is at the end of 2018, when we stopped the run 2. In the last part of the detector, we were already running at the 10 to 20% of transparency. Okay, now up to eta 2.5 or something, wherever we have the tracker coverage, we have the tracking measurements, we have some sort of control over it, that what we are doing. But in these cases, we don't have anything to work with in terms of the tracking. So we don't have any way to reduce the pileup. And then on top of this, when the transparency is lost, your the jets and missing transverse momentum, the resolutions degrade. Those measurements degrade completely. So the present detector components, they have to be upgraded to maintain the physics performance to be an acceptable level beyond the phase 1 data taking. So after run 3, some of these detectors, there is no choice, we have to replace them. Otherwise, we just lose the luminosity. Effectively, that's what it means. So this is just one example. And then knowing the HL-LHC schedule and the parameters, what are the basic requirements for the CMS and Atlas? It's mainly the boils down to the 2 of them. One is the radiation hardness. So here you can see the radiation flux, which will be sort of the cumulative over the HL-LHC operation. And it's equivalent to sort of like the number is 2 into 10 power 16 number, a neutron equivalent per centimeter square. And you see in some of the regions, the radiation exposure is much higher as compared to some of the others, especially the uncapped regions of it. And this really requires the radiation hard detectors. And the high instantaneous luminosity means high pileup. That means per bunch crossing, the number of hard interactions we are getting is much larger. This is just a simulated event of 140 pileup, and the reconstructed vertices is 102 vertices. So this is where you start losing the construction efficiency for vertices also. So the more particle in the events, basically we have the higher detector occupancy. That means we require the higher granularity of the detectors that to just keep the occupancy under control. But this also means that we have to process very large data volumes now. Okay, this is an important it has an important implications. So to improve, we can further improve the performance. This is the minimum we need, but we can further improve the performance by reducing the material in the tracking volume. That's what Chris also mentioned, that we can get rid of some of the material in the tracking volume. Then we can reduce the rate of the nuclear interactions, photon conversions, Bremsstrahlung. Then we can improve the performance of the low PT as well as the high PT physics objects. For example, all these leptons and the B tags and the jets and the missing AT, both for the triggering and for the offline analysis. What does, so just before I move ahead, I just want to quickly mention about the pileup, because whatever the instantaneous luminosity Marcus has just mentioned about, essentially it translates to pileup for us. So this is the pileup distribution for the different years for the run 1 and run 2. And you see how I did not show the instantaneous luminosity plot, but that how the pileup has increased over the time. Okay, so we are already in 2018, we finished at an average pileup of around 37. But in 2016, we also took a special run where the average pileup of the order of 100. So as far as the machinery is concerned, detector is concerned, electronics is concerned, our offline reconstruction algorithms everything worked. But what is the performance becomes the question. Okay, so nothing is breaking down even if you go for the higher pileup. The issue is that the pileup has 2 components. One is the in-time pileup. So basically within the bunch crossing, what are the overlapping other particles which are not of our interest with respect to the hard crossing, hard interaction which has happened. So the way we do it is that whatever the charge particles or the charge tracks reconstructed, they are associated with the interaction of this interest, we remove them. Okay, so this is what we call the charge hadron subtraction, and that's where the trigger plays the most important role. And this is important for the jets measurement, the missing ET, also for the lepton isolation and everything. And there is other one which is the out of time pileup. This is basically what happens is the detector signal develops over the time. It's not just finished in 25 nanoseconds, which is our bunch crossing time. Okay, so you can have, so these are examples I picked up from the CMS electromagnetic and hadron calorimeters from the NCAP regions. And you can see here the red one in this one is the pulse of the interest, and rest of it we get contribution from the other bunch crossings. And the same for the hadron calorimeter. And you can see here the later pulse is, later bunch cross is giving much more signal. Otherwise, I would have just rejected this hit. Okay, so all these things have to be sort of taken care of, and moreover, the neutral particles cannot be sort of handled just by the tracking. So we have to sort of pay attention to that, how to take care of the neutral particles too. So this is the overview of the CMS upgrade plans, and also sort of my outline of my rest of the talk. So the starting point is, and I'm here also mentioning that where Atlas is doing the similar things. So the first component for us to maintain the level 1 trigger, we have to upgrade that. And that involves the data acquisition system and the higher level triggers. And this is the complete replacement. We are trying to sort of include now the tracks in the level 1 trigger at the rate of the 40 megahertz. And I will talk about the numbers a little bit more later. And we're trying to have the particle flow like selections in the level 1 itself, which is essentially a hardware trigger so far. And the Atlas is planning to do the similar things. I mean, they are going for the full replacement. For the tracker, the CMS tracker will be completely replaced, and so is for Atlas. And the basic idea is that it will have the higher granularity of the pixel and the strips, as well as we will extend it to the higher eta regions. It will go up to 3.8 to 4, both for the CMS and the Atlas. And we are enabling the tracking in the L1 trigger. Then we will have in the barrel calorimeters, they will mostly survive. We will be mostly updating the electronics to cope up, like to adjust with the updates in the trigger. And Atlas is also having the new front-end triggers, these trigger systems for their barrel detectors. The Muon detectors we have, I think for the DT and the CSC, which is the barrel part of it, is mostly replacing the electronics, while we are adding more detectors, the new, the GEM, and the RPCs in the forward regions. GEM is the technology which is already in, I mean, one of these stations I've already put in, and it's working right now. Then we are adding this MIP timing detector, which is just the particles passing through the detector and measure this time more precisely. And this is the addition between the tracker and the electromagnetic calorimeter. This is just one layer. In the CMS, we will be adding both in the barrel and the end cap, while in the Atlas, they are only adding in the end cap. This technology is essentially based on, in the barrel, it will be the LISO crystals read out by the silicon photomultipliers, while in the end cap, these are again the silicon based, but some sort of the low gain avalanche diodes. And the CMS is completely replacing is the end cap calorimeter with a high granularity calorimeter, what is popularly known as the HL now. So let's start with the trigger and data requisition. So both in the CMS and Atlas, they will be replacing it. And the issue here is that the muon electron and jet rates would really exceed about the 100 kilohertz at the high luminosity. And that's what we want to check without increasing the PT thresholds. Because the moment we increase the PT thresholds, we lose most of this electroweak precision measurements also. We lose luminosity for that. So we surely don't want to exceed the current ones. And please keep in mind that, okay, whatever we are not selecting a trigger is lost forever. There is no sort of recovery for that. So at trigger, we want to have the events of the interest maximally saved. In addition, there will also be increased backgrounds because of in the muons in the track because of the increased hits. So there is a lot of this confusion matrix which comes in, and we have more fakes because of the accidental coincidence of hits. The solution is that we have to upgrade the trigger system and add the tracking at the level 1 trigger, and also add the new electronics to cope up all this fast data processing, the increased latency, as well as the high data volumes. So that is basically what translates to the high bandwidth and the processing for the triggering. The increase in latency here is that how much time we have to make the L1 decision or the trigger decision to whether to keep the event or not. So the choice of trigger has direct impact on the tracker design, both for the CMS and Atlas experiments. And the idea is here we will be using the latest technologies available in terms of the FPGAs, the ATCA, GPUs, machine learning techniques. But the challenge always is, again, becomes the power delivery, the thermal management, and the system integration. So this is an overview of the CMS trigger setup which we want to have in HL-LHC. The idea is to have that we will have the regional triggers for each of the subdetector system. So for the calorimeters, for the muons, and then we will have the track trigger. But we will also have this additional step, which is like particle flow, like level 1 part. And here, basically, the correlation of the trigger. So this is what we call the trigger correlator. That's where essentially the combination of the different objects will be sort of dealt with. And then we have the global trigger, which will be taking the decision. So the trigger primitives input rate is to the level 1 is of the order of 63 terabytes per second. And the L1 trigger rate, the output should be 750 kilohertz at the 200 pileup, while right now we have it's 100 kilohertz. So our starting point is 40 megahertz, and we are boiling down to 100 kilohertz at the level 1. And what we want to do next is the 750. And the level 1 latency right now is 3.4 microseconds. That's the time we have to make a decision. Now we want to increase it to 12.5 microseconds. And then we have the high level trigger rate, which is right now the 1 kilohertz. That is the rate at which we write to the tape. That those are the events which are available to us for the future further analysis. And now we want to make it to 7.5 kilohertz. So the salient features are essentially the tracking at the level 1 trigger, then more sophisticated algorithms for the pattern recognition. And we have more granular information available both for the barrel and the end cap calorimeters. And these are actually made possible by these high-speed optical links, which are like 10 Gbps links or the gigahertz FPGAs. So let's talk about the tracking detectors. So this is for the CMS and Atlas. This is how the new design looks like, and we will be extending it to up to the 4. The both for the CMS and Atlas, the 8 to the 4. Right now it is of the order of, for the CMS it is 2.5. Now the a lot of development which has gone is to find out the silicon, which is radiation hard. And the final decision also, in addition to that, I mean the manufacturing process itself, we will be, in addition to that, we'll be using the NNP silicon sensors, and they can provide us the high granularity. And then I think the rest of it is more of the, that how the system should be maintained at the low temperatures and the fast data transmission, but keeping the power consumption under the control. So now we will be using the pixel size of the order of 25 by 100 micrometer, the micrometer square. And these thicknesses of the sensors are either 300, and for the pixel it is of the order of 150 micrometer. And this is mainly to keep the radiation damage under control, or the impact of that under control. So just to look a little bit more that what exactly the changes we are doing. So it is not about only the state-of-art technology being used. It's also about how the layout has been updated. And that's where sort of the ingenuity lies. So what we are doing here, so this is the current the tracker system. What is this one is the new one. So the number of layers and number of hits, we want to keep it similar. And you can see here that current CMS tracker is up to 2.5, and then we have with the extended one, this is the part which is completely newly added here, which we have this empty one here. So this one is the 10 times more radiation hard, but as well as it has 25 times more readout channels. And the outer tracker actually uses, you see here, it looks like as if the number of layers are decreasing. That is not the case. It uses the combination of the 2 strip or strip plus microstrip modules, and that I will just talk about in the next slide. So this is the basic idea. The modules which are being used, it has the 2 sensors and placed in a way that they are really close to each other. And in the other ones, it is the silicon strip module as well as the macro pixel module. So there are 2 kinds of modules, and these are called the PT modules. What the idea here is that when the track is, the particle is passing through, you just make a quick decision on whether it is a low PT or high PT, just looking at the sort of direction of it. So just what we are making use of here is the directionality. So if it is bending too much, then what we are expecting from the 2 GeV particles, we just reject them. Otherwise, we just keep them. That's essentially what the idea of the trigger, level 1 trigger stubs is. This will be sort of inputs to the level 1 triggering actually. And the sensor modules essentially looks like this kind of small modules. Now, this way, we can sort of idea here is to select the stubs which are consistent with the particles above 2 GeV, and that way one can maintain sort of data reduction rate which is acceptable to the system. Now, here, one of the biggest challenge will be that we need to know the misalignment between these stubs or the sensors very, very precisely. Otherwise, we start getting the inefficiencies. And And then once we have those stubs, there are different approaches which are being sort of explored. One can go either via the associative memory and FPGA approach, or just the FPGA approach, which seems to be more scalable directly and quite fast. So you start with these stubs. These are the stubs which I just mentioned in the last slide. And you just look for the patterns that what is consistent with the particles which are either greater than 2 GeV or less than 2 GeV, and I reject them or something, or keep them. And accordingly, this is an example that, okay, with the TT bar events of the pileup of 200, the muon efficiency is quite close to 1. Both in terms of the PT or in terms of the eta. And with this, the number of hits are also, the average strike rate is also under control and acceptable to the system. And for the electrons, of course, we have slightly lower efficiencies because of the other interactions which happen in the material. Otherwise, there is no other difference. And the one of the important components was what Chris also mentioned, was the material budget. And you can see here that this is the current one. When it looks into the total material budget in terms of the radiation length. So you see, higher the radiation length, more of the photons will at least convert. So this is what has been reduced by a factor of 2. And this has direct impact on the, and this tracking part also has direct impact on the tracking efficiency, especially in the core of the jet. So you can see here, this one is the current phase 1 tracking, while the phase 2, this is what we are expecting. The same thing for the Atlas, that they have checked the efficiencies, vertex reconstruction efficiency as a function of the local pileup density. And then we also can see the B tagging, that's between the 100 and 140 and 200 pileup, there is not much difference, and that's what we need. So the tracking seems to be doing its job. Now let's come to the timing detectors. How much time do I have? Okay. So coming to the timing detectors, the idea here is that we are getting so this is actually one of the actual data event. It was taken in 2016. It was roughly like 130 vertices. The point here is that we are using the tracking also for mitigating the pileup contributions to the jets. Now here is an example where we see that, okay, these are the particles, these are the jets, the resolution of the jets with the charge hadron subtraction, and this is without. This is how the phase 1 will look like if we just keep on running with the current phase 1 detector. Okay, so the idea here is that to reduce this pileup, what is happening here is that if there are overlapping vertices, then the probability of rejecting the not required track decreases. Okay, so the idea is that if we can look at these also in the time dimension. Okay, so we have these in the time z dimension. This is at the vertices, the positions, but then you try to spread them out in the time also. And that is the basic idea, that if we can make sure and try to see, and this is, I mean, this was quite impressive plot when I first looked at it. And you can see that, okay, there are different, this matching with the simulated ones and nicely the reconstructed ones once you invoke the timing information. Okay, so CMS and Atlas both are looking into adding this MIP timing detector. And for the key requirements for the best timing detectors would be the fast signal rise time, no low signal to noise. But since it is a fast rise time, you also have enough, need to have enough measuring points. Otherwise also it starts giving not proper results. So the CMS and Atlas, they are both going to use the silicon low gain avalanche diodes in the NCAP part. This is what the CMS NCAP one is. And the CMS barrel, we will be using the LISO CE crystal readout with the CPAMs. And the crystal readout, these crystals will be, thickness will be of the order of 3.7 to 2.5 millimeter as we go to the higher eta, just to keep the particle, the travel length same in the, as we go across the eta. And the timing detectors will be mainly used for the time stamping of the tracks and the time of flight of the particles. So this is essentially that how it looks like when we include the timing or not. So the first one is essentially the figure I'm showing here is the efficiency for the prompt muons in Z2 mu events as a function of the number of vertices per millimeter. So sort of line density. And you can see here that without the timing, how it starts decreasing, while we restore a lot of efficiency part just with the timing information, and it has much more dramatic effect in the end cap regions of it. The last one is the B tagging efficiency for a given misidentification in the barrel and end cap, and it gets more sort of flattened out with the timing information included. So then it has, this is one example that, okay, from the GMSB searches, if we have the long-lived sort of particles, the neutrino, then how it translates to the what timing, what decay times we can probe. So this has also quite a bit of gain in terms of the masses. So the timing has implications in almost all of these analyses, whether it's 6 to gamma gamma or the VBF searches. We gain because of the isolation and also because of the vertex identification as well as from the VBF tagging. And then the di-Higgs electroweak SUSY we gain in terms of the signal yield or the reduction in the backgrounds. And then long-lived particles is essentially sort of translates to the timing of these displaced vertices. So the timing capabilities in LHC essentially means increase in the effective gain in the luminosity. So now coming to the high granularity calorimeter. So here what CMS has decided to go for is a sampling calorimeter, which is based on the silicon and the scintillators. So the electromagnetic calorimeter part is essentially the this one, the silicon sensors with interspersed in the absorbers of the copper, tungsten, or the lead. While the later on part, the hadronic calorimeter, the absorber used is the stainless steel, but in the regions of high radiation exposure. So this part, we have the silicon, otherwise we are using the scintillators. So these are the nice scintillator tiles of the order of 2 by 2 centimeters square and read out directly by the silicon photomultipliers. So this detector actually allows us to go for sort of a 5D calorimetry, and it's ideal for the particle flow reconstruction techniques, and this I will sort of comment on in my next slides. The full system has to be maintained at -30 degrees, and that's one can see that one of the drawbacks or the challenge. And this one will total give us the 6 million silicon channels and 240 scintillator channels. And by the way, this one, the whole effort is actually driven by the CALIS activities, and that's how we started with. And we are still closely interacting with them, which I will show. So this is one example case that where the HL helps. So this is one sort of example of the Higgs going to gamma gamma in the VBF channel. And this event display here is showing that the one photon and the one jet is in the same quadrant. So this is supposed to be the rest of it is piled up. And once you apply the timing cut of the 90 picoseconds, just from the HL information, HL readout, we get rid of most of the pile up. And you can see how clearly the two blobs show up. And this is still not using, this is before using any MTD information. And we expect it to get better with the MTD requirement. And you can see this is in the high eta regions because it is the end cap detector. And when I said that it's a 5D calorimetry and it's really an imaging calorimetry, what I mean by here is essentially this example. Here, there are two particles being shot in the detector. These are the two tau leptons decaying hadronically. So we have one of the taus going to 3 pions, another one pi 0 and pi channels. And you can see here that you try to cluster using all these records with the graphical neural networks. And you can see here that the nicely matching clusters sort of show up in the detector. So right now it is just the simulation that what are the sort of the simulated clusters and what are the sort of the predicted ones from this one. And it is also able to predict some of the noise stuff. Now, this is all in the sort of the simulation, but then how do we trust it? And that's where we are doing dedicated test beams for this one. We did it one in the 2018, where we actually exposed the whole system to the electrons and pion beams of the 22-300 GeV. The idea was that we have the silicon sensor modules for the end cap, the ECAL part, the electromagnetic calorimeter part. Then we had this daisy-like structure for the hadron calorimeter part. And then we have, this is the scintillator based, and this actually prototype came from the CALIS AHCAL. Okay, so this is what I said, the close collaborations are still going on the calorimetry side of it. And here is just the results from the test stream, that this is one pion shower through that system. And you can see the data and simulation, even out of the box, they are sort of nicely matching. And then we had sort of, these are the results from the test beam, which are going in this paper, the upper ones, which are using just a simple chi-square method. But when we apply the graphical neural networks and start exploring more the granularity of the detector, we start having a lot of like a factor of 2 improvement in the resolution itself. And this is for the pions. This is not only simulation, but also the data we took in the test beam. And what we are doing now is trying to understand where the improvements are coming from and what we are benefiting from the using the graphical neural networks, what we are benefiting from the leakage, how much we can learn, and the trying to sort of disentangle the various effects which are going on in the improvements. So I think I am almost done. So just a quick note on the upgrade of the Muon detectors. The key point here is that the precision measurements crucially depend on how well you can measure your muons. So what we are doing in CMS is upgrading the end cap part of it. Here, the additional GEM chambers are being installed. That is in the plan, and that essentially, including ME0, extends the full coverage to of the order of eta to 2.0 to 2.8. So the main upgrade for the barrel part and the rest of it is on the electronics. That the whole electronics board will be replaced to be consistent with the triggers, and for the rest of the we are just extending the muons to the higher eta regions, and that has direct implications on the rates we can. So upper one is showing the level 1 efficiencies as a function of the true muon PT. So we have quite a bit of improvement as compared to the phase 1. The black one is for the phase 2, and the same is for the end cap regions where the improvements is high. And overall gain we have in the factor of 2 reduction, basically factor of 5 to 10 reduction in the level 1 trigger rates. And it is much more in the case of the end caps. So this has the direct translation again to the channels like Higgs to ZZ, where if you have 4 muons, going from 80% efficiency to 90% efficiency makes a huge difference. And that's what the basic idea about these, the basic motivations for these improvements to the muon detectors are. And many of these analyses, which are like either going to Higgs to ZZ or double pattern scattering or tau going to 3 muons, Drellian, forward backward asymmetry, all these benefit by a factor of 7% to 15% in the various channels in terms of the performance. So just to summarize, the LHC experiments are well on the way to update detectors and the triggers DAQ system to cope up with the challenges of HL-LHC. Lots of test beam studies are going on, both at the small scale lab test as well as the big scale test beams. The radiation hardness and the precision timing capabilities are sort of the key to deal with the HL-LHC challenges. The fast readout electronics and triggers to handle the large data volumes. For the FCCS, the HH, the radiation hardness and pileup are the default challenges, but also we will need good coverage to the forward detectors, because the physics, the way it is that, okay, fine, we are probing more low X physics as well as more in the forward direction. So there the precision of muons up to eta 4 and calorimetry up to eta 6 will be the key. Right now we are going only up to 3, and forward detectors we have with lesser resolution. The cross collaboration among the FCC related activities or ILC related activities are going on wherever they are applicable or possible. I think that's it. Thank you. Sorry if I took longer.
Okay. Oh, great. Lots of questions. That's good.
Hello.
Yeah.
So you talked about usage of graph neural networks. So will that be used in will that be used in, say, for example, in tau tagging or something like that? Like you showed an example of that.
I showed an example as an illustration of the power of the detector, that how much information we have, but it can be used anywhere and everywhere in principle. And there are studies going on.
Okay.
So those, I think, various studies are also available from the CMS where we are using some of these techniques. They are not in the default reconstruction right now.
Okay.
But these are all available.
Okay. And how much improvement can we expect from the current methodologies of say tau tagging or B tagging, something like that?
For run 2, I don't have or run 3, I don't have the numbers in my head right now.
Okay.
Okay.
Thank you.
So when you talk about radiation hardness, so what is not available as of now? Hardware or the radiation up to that level? Why we are not able to harden our hardware?
So
radiation.
I think if only talk about the radiation hardness, it will have different sort of effect on different kind of detectors, right? For the electromagnetic calorimeter, I showed that scintillators, it was the transparency which was getting affected. For the silicon, it might be the bulk damage which will happen, right? So as we are, if we continue to run with the same detector, I think they will become useless for us. Let me put it this way. They will not be as performing as we need.
So where we are falling short?
It's the material, the detector material itself, right?
Material.
So some of them is that part. The other part is that if we increase that's what the luminosity detectors are, not radiation hardness. But I don't think there is an current electronics part, how much that can be affected. So for example, the current tracker, it will not be able to sustain after the run 3. We will have to replace it. Pixel we already replaced in 2016 or 17.
Okay, thank you.
So how are we going to deal with the neutral pileup at L1? So you talked about tracking, so we can deal with the charged pileup.
Yeah,
But what about neutral pileup at L1?
that will be limited as of
So
now.
we won't have anything like
We
puppy.
can do on an average. You can do on an average, right? That we do even now also in all the lepton isolation, all in the jets also, we have on an average subtraction of the neutral pileup.
Okay, so
Right,
something
but
like
at
puppy
the-
can be implemented at L1.
It can be, but no puppy, I don't know whether it's L1 or not. That I have to check. But the HLT definitely. But then I am hoping that okay, this timing improvements which are getting at the subdetector level, for example, the ECAL or for the EGCAL or from the the calorimeters mainly. I hope some of this information can be used, and that will help us.
Okay.
Because the calorimeters, essentially you don't need only charged particles. You need the total energy deposit, and that matters.
Also, can we use MTD at L1, like MTD information at L1?
I don't think so. We are not using L1 MTD, right?
There's a circuit in the front end electronics for it, but it was not.
Yeah, it was not,
It's provisional, but it's not part of it.
it will come up. I think when some of the people will get free from the ongoing activities, then we'll put MTD also in L1.
Ma'am, for FCCHH, like when we design the detector, like let's say a replacement detector like CMS for FC, because the whole geometry will be different. So what sort of like size, detector size, or changes do you expect? Like, can you comment on something on that? Like if when you build the detector for the FCCHH, like what will be the dimensions and
Dimensions, so one of the consideration you need to have is that, okay, we will have more high energy particles there, which you
Yes.
have to stop, right? So you need enough stopping power. But for the calorimetry, you don't have to double the detector, right? It goes logarithmically.
okay.
So it's not that, okay, fine, whatever calorimeter we have to double the length.
Yeah, no,
of it.
because like at 100 TeV, the boost
So-
effect will be more. So like
Boost
for,
effect will be more, but if you're talking about the sort of the key component which will come in the terms of the calorimetry, there we have to sort of make it sufficiently thick, but it will not be a huge difference.
okay,
So it won't double the depth of the detector. That's what I'm saying, because it will go only as the log A.
okay.
Okay, for a last question.
Yeah. Are you happy with just up to eta 3
Which one? The
coverage? You
For
only
the-
talked about the end cap, okay? What happened to in the forward detectors? Would they survive?
forward detectors, the HF you're talking about, that seems to be sort of fine. There's no issue with that. As far as I know, I am not sure of the
Are you
electronics part. Of
sure
it.
about that?
I'm not sure of the electronics part of it.
No, even the detector part of it.
Okay, but
It
we are
has-
not
It also
replacing it.
gets the radiation
Yes,
damage.
yes. But as far as I know, the quartz fibers, we are not replacing them. But yeah, I would go by your words if you say so.
No,
Yeah, but I have not
they
come
must
across.
survive, okay?
I have not come across the discussions about replacing the forward ones.
Yeah, I do think, it's, I can't remember if it's 4.5 or 4.2, but
Up to that.
definitely
Yeah.
it's actually the cladding that,
The
Fails.
quartz fiber cladding part.
Yes, also it needs, okay, something in front of it, okay? Otherwise, yeah,
I didn't get your last point.
it needs something in front of HF.
Okay.
yeah. No, I think there are some proposals that, it is tricky. I think that the, full Cherenkov calorimeter was great achievement. I don't think we had one before, but it still wasn't good enough to survive the HL-LHC. Let's thank Seema again.
Thank you.